What is the expected number of exposed faces if one of the n cubed smaller cubes is selected at random? Now n is some positive integer, and off to the left here you can see we have a 4 by 4 by 4 set of these little cubes all put together. So this is the case of n equals 4. A familiar case is n equals 3. That is one of those Rubik's cubes that you might have seen in the past. So the question here is, how many exposed faces are there? In fact, what is the expected number of exposed faces if you pick one of these little tiny cubes? And in this case there are 4 times 4 times 4. There's 64 little tiny subcubes here. And you're going to pick one at random and say how many exposed faces are there. Well, here's the beginning of the analysis. First of all, there's different types of cubes that are out there, and let's start with the corner cube. I will go ahead and shade the exposed faces if you happen to get one of these corner cubes. And by the way, there are always 8. No matter what n is, there's always going to be 8 corner cubes here. And if you get one of those corner cubes, you get 3 exposed faces. So it has the most exposed faces. Now let's go to an edge cube. An edge cube might be this one right here. Not a corner cube, but it lies on one of the edges of the cube. And how many of those are there? Well, there are 12 times n minus 2. If you think about the geometry, there are a total of 12 edges here, and that gets multiplied by n minus 2 such, and each one of those has 2 exposed faces. The next one is a face cube, and I will go ahead and pick this one right here as the face cube. A face cube has 1 exposed face, and there are n minus 2 squared times the 6 faces of those cubes that are out there in this particular arrangement. And finally, the last one is an interior cube. I can't shade an interior cube because you can't see them here, but those interior cubes don't have any exposed faces, and there are n minus 2 cubed such interior cubes. So if we let the random variable x be the number of exposed faces in a random cube, a random small cube selected, then it will have probability mass function. Notice here for the support you can have 0, 1, 2, or 3 exposed faces, and the probability of getting 0 faces is going to be n minus 2 cubed, that's the count of the number, divided by the total number of little small cubes, and there are always going to be n cubed small cubes. Likewise, you can take your 6 times n minus 2 squared, divide it by n cubed, and that will correspond to x equals 1 exposed face. 12 times n minus 2, that also gets divided by n cubed. That corresponds to 2 exposed cases. And finally, 8 over n cubed corresponds to 3 exposed cases. Well, the expected value of x in this case will be each of the mass values, 0, 1, 2, and 3. It'll be a summation multiplied by their associated probabilities. So this is 0 times f of 0 plus 1 times f of 1 plus 2 times f of 2 plus 3 times f of 3. And when you work through all of the algebra, this thing reduces to just 6 over n. So one question that might come up is, why is the limit as our big cube here gets bigger and bigger and bigger, in other words, as n grows, why is the expected value of x in the limit 0? And the answer to that question is as follows. If you take the limit as n goes to infinity of your probability, which is right up here, of getting an interior cube. If you take the limit of as n goes to infinity, you will see that this right here goes to 1, which means as your cube gets bigger and bigger, your probability of getting an interior cube goes to 1, and that is why your expected number of exposed faces goes to 0.